Good day, I'm Mr. Robin Aldo. Today, I'm going to discuss concepts and applications of the following topics for the course Advanced Quantitative Research Methods. The following topics are hypothesis testing, students' t-tests, test sign, points estimate, and confidence level. ANOVA, analysis of variance. But let's start with the idea of research. What is research? Research plays an essential role in the continuous growth and development in all aspects of ever-changing world. It is a process of asking meaningful questions about a certain topic or subject, using reliable resources to seek for the answers, and sharing the results as its implication to others. Research serves as a tool for establishing knowledge and efficient and valuable learning. Through research, it helps us understand the society as a whole, its norms, cultures, policies, code of conduct, trends, preferences, and the like. Research helps us discern correctly, understand various issues, prove lies, and support trusts. Through research, we can come up with valid predictions, theories, and great results through thorough observations, hypotheses, and research queries. These things lead us to arrive with meaningful conclusions and generalizations. And most importantly, it is seed to love reading, writing, analyzing, and sharing valuable information. Now, the question is, how can we come up with meaningful research? Take note of the term, meaningful research and substantial research. One of the means to come up with substantial and extensive research is through incorporating descriptive and inferential statistics. During the midterm period, I was able to discuss thoroughly descriptive statistics through writing. Now, we will be focusing on inferential statistics. Moving on. Inferential statistics. Inferential statistics allows us to use what we have learned from descriptive statistics, using gathered data and the resulting descriptive statistics, such as mean, median, mode, range, standard deviation, variance. Inferential statistics extend beyond the immediate data. It helps us to infer from the sample rather, what the entire population might think. Furthermore, inferential statistics are also used to make judgments about the probability that an observation or a certain phenomenon is dependable and reliable, or it's just happened by chance. There are some cases that we make a claim just because we experience it once. I myself is guilty of these kinds of things. There are times that, you know what? This thing is not true because this what happened to me. Oh, you know what? It's really true because it happened to me. But inferential statistics now will help us arrive with reliable results that, okay, it just happened by chance. Okay, it really happened because it's true. Or it didn't happen to me. It's not true. But if inferential statistics tells us that it's really true, then It's just happened that by chance it didn't happen to us. Let's say, for example, setting aside the joke. Let's say if I think that I'm actually handsome because someone told me that I'm handsome, I cannot just claim it because someone told me, or just one person told me. I have to ask other people to rate me in order for me to say that I have really reached the standards to be said that I'm really handsome. Good. Moving further. Let's have an example. Fast food restaurant always delivers on time. So, person A hypothesized that fast food restaurant A always delivers on time. These can be tested by gathering enough data, which is the descriptive statistics. Through ordering to that restaurant for a couple of times, then use inferential statistics to analyze and interpret the data. We use inferential statistics to make inferences from our data to more general conclusion. There are two major divisions of inferential statistics: confidence interval, test of significance, or hypothesis testing. But let's focus on the hypothesis testing. What is hypothesis? And what's hypothesis testing? A hypothesis is a theory or proposition set forth as an explanation for the occurrence of some observed phenomenon, asserted either as a provisional conjecture to guide investigation, called a working hypothesis, or accepted as highly probable in view of the established facts. Statistical hypothesis testing, also called confirmatory data analysis, is often used to decide whether experimental results contain enough information to cast doubt on conventional wisdom. Let's have an example. It is still believed that men are better in English. It's the other way around. Men are better in math, while women are better in English. Because they're saying that, because women are more expressive, so on and so forth. But after thorough research, they found out that men and women have same potential when it comes to mathematics, because math is a skill and not by gender. So, even if you believe that, hey, wait, I think men are better in math than women because I'm a man and my seatmate is a woman and I got better grades than her. No. Through inferential statistics, they were able to gather more data to come up with more reliable and dependable results. Moving on. Let's have null and alternative hypothesis. Before testing for phenomena, you form a hypothesis of what might be happening. Your hypothesis or guess of what about occurring might be that certain groups are different from each other, or that intelligence is not correlated with skin color, or that some treatment has an effect on an outcome measure. For example, from this there are two possibilities: a null hypothesis that nothing happened, or there were no differences or no cause and effect, or that you were correct in your theory, which is labeled the alternative hypothesis. In short, when you test a statistical hypothesis, you are trying to see if something happened and are comparing against the possibility that nothing happened. Confusingly, you are trying to disprove that nothing happened. If you disprove that nothing happened, then you can conclude that something happened. Once the statistics are collected and you test your hypothesis against the likelihood of chance, you draw your final conclusion. If you reject the null hypothesis, then you are claiming that your result is statistically significant and that it did not happen by luck or chance. As such, the outcome proves the alternative hypothesis. If you fail to reject the null hypothesis, you must conclude that you did not find an effect or difference in your study. Thus, this method is how many pharmaceutical drug and medical procedures are tested. Let's say, for example, let's have the different types of error. Type 1 error. The first kind of error that is possible involves the rejection of a null hypothesis that is actually true. Let's say, for example, for this funny but very meaningful example, this is a type 1 error which is called false positive. False positive because look at what the doctor mentioned. You're pregnant. It's something positive, but it's false because he said that to a man. So, this is an example of a type 1 error. We actually, so HO is true, type 1 error, and yet we reject the null hypothesis. Test 1 error can be controlled. The value of alpha, which is related to the level of significance that we selected, has a direct bearing on type 1 error. Alpha is a maximum probability that we have a type 1 error. For a 95% confidence level, the value of alpha is 0.05. This means that there's a 5% probability that we will reject a true null hypothesis. In the long run, 1 out of every 20 hypothesis tests that we perform at this level will result in a type 1 error. Type 2 error. In a type 2 error, the other kind of error that is possible occurs when we do not reject the null hypothesis that is false. This sort of error is called type 2 error and is also referred to as an error of the second kind. Type 2 error are equivalent to false negative. So if we're going to look at this funny but very meaningful example and relevant, you'll notice that the doctor mentioned that to the woman that you're not pregnant despite that she is. So false negative. Not true, and at the same time it's like the negative because the message also is negative to a woman who is expecting a child or to bear a child. If we think back again to the scenario in which we're testing a drug, let's say, what would a type 2 error look like? A type 2 error would occur if we accepted that the drug has no effect on the disease, but it really did. So, how are we going to avoid committing errors? Type 1 error and 2 errors are part of the process of hypothesis testing. Although the errors cannot be completely eliminated, we can minimize one type of error. Typically, when we try to decrease the probability of one type of error, the probability from the other type increases. We could decrease the value of the alpha from 0.05 to 0.01, corresponding to 99% level of confidence. However, if everything else remains the same, then the probability of a type 2 error will nearly always increase. Many times, the real-world application of hypothesis tests will determine if we're more accepting of type 1 or 2 errors. This will then be used when we design our statistical experiment. Now that we have learned the type 1 and type 2 errors, let's proceed to the different types of tests. We have z-tests and t-tests. We should learn about these two types of tail tests. One tail test determines whether a particular population parameter is larger or smaller than some predefined value. Uses one critical value or test statistic. Two-tailed hypothesis determines the likelihood that a population parameter is within certain upper and lower bounds. May use one or two critical values. To make this more understandable, I'll give you an example. If you're trying to compare, let's say, I believe that I am more intelligent than any of my classmates. That is an example of a one-tailed hypothesis. Because it's just either higher or lower. That's it. But what about if it's two-tailed tests? So, it's just that determines the likelihood that the population is within certain upper-lower bounds. To make it more understandable, let's say, for example, I believe that my IQ is not equal to my classmates. You're just saying not equal, but you are not saying if it's higher or lower. So if it says, oh, they're equal, meaning even if you got a 97 while they got a 95, still it's just a matter of difference in the number, but it just has the same message that you have the same IQ level. But you will not claim that it's either you're less or better than that. Moving on, the z-tests. Z-test refers to an invariant statistical analysis used to test the hypothesis that proportions from two independent samples differ greatly. It determines to what extent a data point is away from its mean of the data set in standard deviation. The researcher adopts z-test when the population variance is known. In essence, when there's a large sample size, sample variance is deemed to be approximately equal to the population variance. In this way, it is assumed to be known, despite the fact that only sample data is available and so normal tests can be applied. The assumptions are all samples, observations are independent, all sample size should be more than 30, distribution of z is normal with the mean 0 and variance 1. Let's have an example. A car manufacturer is trying to lower the amount of defect it has in its cars. Two distinct assembly procedures are used to build cars. In a sample of 350 cars coming off the line using the first procedure, there were 28 with major defects, while a sample of 500 cars coming off the second assembly line shows 32 cars with defects. Is the difference between the two assembly procedures significant? So, how will we know if this is an example of z-test? First, if it's more than 30 sample means. Look at the means here. So, if in a sample of 350, in a sample of 500, since it's more than 30, then we can use the z-tests. Move on. Let's have the t-tests. The t-test is a hypothesis test used by the researcher to compare population means for a variable classified into two categories depending on the less than interval variable. More precisely, a test is used to determine how the means taken from two independent samples offer. T-test follows t-distribution, which is appropriate when the sample size is small and the population standard deviation is not known. The shape of a t-distribution is highly affected by the degree of freedom. The degree of freedom implies the number of independent observations in a given set of observations. The assumption of t-tests. All data points are independent. The sample size is small. Sample values are to be taken or recorded accurately. This is the example. In a level average of IQ is 100, a sample of 30 who have taken the medication So since the sample size is just 30, then we can use the t-test. Let's continue. Let's now try to compare. The t-test can be understood as a statistical test which is used to compare and analyze whether the means of two populations is different from one another, or not when the standard deviation is not known. As against, z-test is a parametric test, which is applied when the standard deviation is known to determine if the means of the two data tests differ from each other. The t-test is based on students' t-distribution. On the contrary, z-test relies on the assumption that the distribution of sample means is normal. Both students' t-test distribution and normal distribution appear alike, as both are symmetrical and bell-shaped. However, they differ in the sense that in a t-distribution, there is a less space in the center and more in the tails. One of the most important conditions for adopting t-test is that population variance is a known. Conversely, population variance should be known or assumed to be known in case of a z-test. Z-test is used to a sample size is larger than 30, and t-test is appropriate when the sample size is small in the sense that it's equal or smaller than 30. Point estimate and confidence interval. Estimation is the process of generating inferences from a sample about an unknown population parameter. An estimator is a statistic that is used to infer the value of an unknown parameter. Point estimate. A point estimate is the best estimate in some sense of the parameter based on a sample. It should be obvious that any point estimate is not absolutely accurate. It's an estimate based on only a single random sample. If repeated random samples were taken from the population, the point estimate would be expected to vary from sample to sample. A point estimate is a type of estimation that uses a single value, oftentimes a sample statistic, to infer information about the population parameter as a single value or point. A point estimate, particular value of an estimator used to predict the population value. For example, an estimate of the population mean from the sample mean may be 14. Another example. So if you're going to identify actually the mean, then this is an example of point estimate. Estimate because it actually doesn't give you an exact value, but an estimate of the population mean. So your point estimate for the mean length of all magazines advertisement is 12.4 sentences. Confidence interval. Here's an old joke. A guy notices a bunch of targets scattered over a barn wall, and in the center of each, in the bullseye, is a bullet hole. Wow, he says to the farmer. That's pretty good shooting. How do you do it? Oh, says the farmer. It was easy. I painted the targets after I shot the holes. Confidence interval are a little like that. After we make a point estimate, a bullet hole, we are going to draw a target, an interval, around the point and state the probability that the real object is in the target area. The wider the target, the greater the probability. And so you would expect also the more accurate the shooting, the greater the probability. To avoid misleading you, we should rephrase the joke. Suppose there's only one target painted on the barn and all of the bullets holes are within it, even though they're not all in the center. The center is defined by the mean of the bullet holes. The size of the target is defined by the variance of the collection of bullet holes. It's still pretty good shooting, and the better the shooting, the smaller the target needs to be to encompass them all. We can then estimate the probability that the real objective is in the target area. Confidence interval is an estimate constructed on the basis that a specified proportion of the confidence intervals include the true parameter in repeated sampling. How frequently the confidence interval contains the parameter is determined by the confidence level. 95% is commonly used and means that is repeated sampling. 95% of the confidence interval include the parameter. 99 is sometimes used when more confidence is needed and means that in repeated sampling, 99 of the intervals include the true parameter. To sum up, a point estimate is a single number. A confidence interval provides additional information about variability. If this is the point estimate, the confidence interval are in this line. Lower confidence limit, upper confidence limit. Analysis of variance, or commonly known called as ANOVA. In real life, things do not typically result in two groups being compared. It can be more. ANOVA is used to compare the means of more than two populations or samples. Two-sample t-test is problematic because it just increases the risk of type 1 error. When to use ANOVA? Data must be experimental. With many experimental designs, the sample sizes must be equal to the various factor level combinations. A regression or analysis will accomplish the same goal as an ANOVA. Assumptions. The expected values of the errors are 0. The variances of all errors are equal to each other. The errors are independent. They are normally distributed. Examples of when to use ANOVA. Commission only, fixed salary, combination of the two. If we are actually looking at the salary, what are the things that we need to consider? These three things. Since we are now comparing three things than the two, then it is more suggested and recommended to use ANOVA. What else? A group of psychiatrists is trying 3 different therapies. They want to see if one therapy is better than the others. Which is better? Counseling, medication, biofeedback. Students from different schools took the same standardized test and want to see if one school outperforms the others. One-way or two-way? One-way or two-way refers to the number of independent variables in your analysis of variance tests. One-way has one independent variable with 2 levels, and two-way has 2 interdependent variables. It can have multiple levels. For example, one-way analysis of variance could have 1 for brand of cereal, let's say IV, and two-way analysis of variance has 2 IVs, brand of cereal and calories. One-way ANOVA. One-way ANOVA between groups used when you want to test 2 groups to see if there's a difference between them. Example. Are there differences in GPA by grade level between freshmen, sophomores, and juniors? Since we are comparing 3, then we have to use ANOVA. Two-way ANOVA with replication. Two-way ANOVA without replication, used when you have one group and you're double testing the same group. Example, you're testing one set of individuals before and after they take a medication to see if it works or not. Two-way ANOVA with replication. Two groups and the members of those groups are doing more than one thing. Example, two groups of patients from different hospitals trying two different therapies. Two-way ANOVA. Example, are there differences in GPA by grade level? Freshmen versus sophomores versus juniors, and gender, male versus female. From this presentation, we have learned things such as z-test, t-test, hypothesis testing, statistical hypothesis testing, ANOVA, or analysis of variance. We have also learned point estimates and confidence intervals. This is the end of the presentation. I hope you have learned something from today. See you soon!